Assalamu alaikum. Welcome to this new series of time series data analysis in STATA. So, my dear followers, students and colleagues, I have created a new playlist on my YouTube channel that is titled as time series analysis in STATA. And this is the first video of its series in which I am going to check stationarity of time series data as well as selecting leg length. So I'll be doing this, and in the coming videos I would like to estimate cointegration and error correction model, and that will be followed by vector autoregression, and later on I'll estimate autoregressive distributed leg models and others as well. So here is my data. This is my data file, and in this data file I have data on income, investment, consumption, and then I have also taken natural log of all these three variables, and later on I have taken the first difference of log of income, difference of log of consumption, and difference of log of investment. So let me summarize, and this is the summary of these variables, and these are the this is income. The total number of observation is 92. This is income, this is investment, this is consumption, and this is quarterly data, and this is a log of investment. This is a first difference of log of investment. This is log of income. This is first difference of log of income, and this is log of consumption, and finally this is first difference of log of consumption. So first of all, I would like to set this data as a time series set, and since this is quarterly data, so I will write QTR. So I have set this as time series data. Now I will start with the checking stationarity of the log of income variable. So I am using, this is the Diki Fuller test of the log of income, and this is the McKinnon approximate p-value for this test. Since this value is much higher than 0.05, so we fail to reject the null hypothesis. We fail to reject the null hypothesis, and we conclude that the series of log of income has a unit root, that is, it is non-stationary. After this, I would like to test log of investment for stationarity, and again this is the test results. This is the first, the 1% critical value, this is the 5% critical value, and this is the 10% critical value. This is the test statistic, and here is the p-value, McKinnon approximate p-value for ZT, and since again this is greater than 0.05, so we retain the null hypothesis, and we conclude that the series of natural log of investment is non-stationary, that is, it has a unit root. And after this, I would like to check the stationarity of the first difference of log of income with the Diki Fuller test. So now this time this p-value is less than 0.05, so we reject the null hypothesis of unit root. So it means that when we take the first difference of the log of income, then it becomes stationary. Similarly, I can also check the same for first difference of the log of investment, and instead of income I am using investment, and this also is now stationary because the p value is less than 0.05. So it means when we checked the stationarity of the log of income and log of investment in its level, both of the series were non-stationary, they had unit root. But when we checked its stationarity by taking the first difference, then both, that is the first difference of the log of income and the first difference of the log of investment, both became stationary. We can also check the same using Phillips-Perron test, and here is the Phillips-Perron test for the log of income. And again, the p-value, the Mackianian approximate p-value for this is greater than 0.05. So this test also shows that the log of income has a unit root, that is, it is non-stationary at level. We can also check this for log of investment, and this p-value, which is 0.65, that is greater than 0.05. So on the basis of this p-value, we conclude that the natural log of investment has a unit root, it is non-stationary based on Phillips-Perron test. So this is how we can do that. Now let me check this for the first difference of the income, that is the first difference of the log of income, and this is Phillips-Perron test. Now this p-value is less than 0.05. So now it became stationary. And similarly, we can also do the same for Phillips-Perron test for the first difference of the log of investment, and its p-value is now 0.00. So we reject the null hypothesis of unit root. So we conclude that the time series of log investment, natural log of investment in its first difference doesn't have unit root, that is, it is now stationary. After this, I would like to check the selection order criteria for both the variables. So I am using this command VARSOC, that is variable selection order criteria, and I listed the two variables, that is natural log of income and natural log of investment. And if I press, so according to this criteria, 4 criteria, that is FPE, Akaike information criteria, and these two other criteria, Hanian and Schwarz Bayesian information criteria, they show that the selection order criteria to be used is the first leg, that is we will use the first leg in this series. And after this, let me check the long run relationship between the income and investment variable. So look at this. This is the OLS regression of natural log of income and natural log of investment. The total number of observations is 92. The F statistic value is 3236.66, and its P probability value is 0.00. So it means that the overall equation is significant. The R squared value is 0.97, that is 97% of the variation in the natural log of income is explained by natural log of investment. The adjusted R square is almost the same but a little less than R squared. And this is the total sum of square. This is the regression sum of square, or model sum of square, or estimated sum of square, or explained sum of square, and this is unexplained or residual sum of squares. And this is the coefficient of investment, and it shows that if there is 1% increase in the investment, there will be 1.15% increase in natural log of investment, other things remaining the same. And this is significant, highly significant. This is its t value, and this is its p value, and this is the consumption, this is the constant of this regression. And after this, I can predict residual U hat RESID. Now this is residual. So I can check the some tests for this. So let me first check the HET of UHAT. So there is no problem of heteroscedasticity in this problem, and I can check Shapiro-Wilk for RESID rigid SWILK comma U hat. Sorry, I used rigid. I should use U hat. And this also shows that the residual follows normality because the p value is greater than 0.05. I can also check the White test for this. However, this test shows that there is a problem of serial autocorrelation in this model. So I hope this is very informative for you, ladies and gentlemen. In the coming video, I would like to show the short-run relationship between investment and income. In this video, I discussed the long-run relationship between investment and income, and let me also show that in my this is the long-run relationship. The short-run relationship will be shown in a separate video. So the natural log of income is regressed on natural log of investment, and the coefficient of natural log of investment is 1.149. So it means that 1% increase in natural log of investment will increase income by 1.15%. This is the standard error of this coefficient, and this is the t value. The r squared value is 0.93 and the adjusted r square is 0.972. The f state value is 3236.66, and based on this p value we conclude that the overall equation is significant. So this is very interesting. I thank you for your attention. If you haven't yet subscribed to this channel, kindly subscribe to the channel, and also click on the bell icon, and then you will get information about other videos that I'll upload. Thanks once again for watching my video and channel. Kindly share this channel and videos with your